Hydrogeophysics, there are two words in it. You have the geophysics itself, and then you have the hydro. So basically, we're going to apply geophysical methods to anything that could be related to water. I don't know if you are all familiar with geophysics. I like to start my lecture with that kind of picture. I don't know if any of you knows what you are looking at. It's not too difficult, right? Do you know what it is? Yeah, it's a brain, but do you know how you get such an image?
MRI.
It's MRI, so it's basically nuclear magnetic resonance. I heard it. And yeah, I like to make a comparison between geophysicists and radiologists, basically. Because we're doing the same job. We're trying to look inside something. It's just the radiologists, they're trying to look into the human body, and we're trying to look down the earth. Actually, this second picture that you see here on the right, which is just a profile of water content over depth, is collected with the same method as this image. The difference is that when you do it on the human body, maybe you have been in an hospital, you know how it looks like. It's like a big tube. You can go, you put your head into it, and then you have sensor everywhere, so they can have the sensor at different locations, so they can have a very high resolution image of your brain. And what we're doing is much more complicated because we are at the Earth's surface and we're trying to look into it, and we cannot put our sensors everywhere, right? It's too costly. You have to drill boreholes, you have to put your sensor in those boreholes. It's really too costly. What we want is to have like cheap images of the subsurface. And of course, by doing that, we have much lower resolution that what you could get with the human body. So I'm not going to talk about nuclear magnetic resonance today, but it's just to give you an idea of what kind of things we can do. I also want to start with a disclaimer. I mean, you might see in my presentation a few nice images, like this one. Okay, it's nice. You have colors, you have numbers, you have things changing. It looks like it's nice, yeah, but what is it? Could any one of you tell me what this is, actually?
The electrical resistivity. I mean, it's our...
Yeah, it's the work we did with the practical. So I have my team, we do the practical in the afternoon. So of course they know what they did. We collected some data, we inverted them, and then we get a nice picture. But if you don't know the context of this, there is no way to start making an interpretation, right? I mean, it's just numbers, colors, things changing. So I have to tell you, of course, I'm a geophysicist, I like doing geophysics, but if you do it without knowing what you're looking at, it's just useless. So it's really important to know that the context is so important, and that you never interpret a geophysical data set or geophysical image alone. You need ground truth data, you need prior geological knowledge, and so the geophysicist is never alone. Or you're a very good geophysicist, who is also a geologist and maybe an hydrogeologist, and then you can do it on your own. But typically you need a team to help you in the interpretation. Hydrogeophysics is a big topic, so today I'm only going to focus on two types of methods which are sensitive to the same parameters, which is electrical resistivity. And I'm going to talk about electrical and electromagnetic methods. This is what I'm going to talk about. Hopefully, I'm going to manage to at least tell you a little bit about those first 10 points, and I will see if we have time also to do the electromagnetic at the end. We'll see. I'm trying to go not too fast. But yeah, let's start with the beginning. Electrical and electromagnetic methods, they're sensitive to physical parameters, which is called the electrical resistivity, which is basically the property characterizing how easily an electrical current can flow through a given medium. If the electrical current can flow easily, we'll have a low resistivity, and if it cannot flow easily, we'll have a high resistivity. I'm going to use the notation rho, so don't mess it up with density, for which we're also using rho often, and the unit is ohm meter. I'm going to switch once in a while between resistivity and conductivity. Basically, it's the same property. It's just that the conductivity is the inverse of the resistivity, and then we're using Siemens per meter. The reason why we are using the 2 is a little bit historic, but you don't have to know that. Well, in practice, it's very difficult to measure the resistivity of something. It's a property which is difficult to get. What we can do is, going back to high school, I'm sure you have seen this beautiful law which is called Ohm's law. What you can have access to is to access the resistance of a given sample. So basically, in Ohm's law, if you apply a difference of potential between the two ends of a given sample, and that you inject a given current through it, you are going to be able to deduce the resistance by taking the ratio of the difference of potential over the injected current. And this is what you can actually measure on the field. You can measure resistance. And the way you get to the resistivity, if you have a sample, it's relatively easy because you can apply a geometrical law to that. Basically, the resistance of a cylindrical sample would be its resistivity multiplied by the length of the sample and divided by the cross-section. So it's work also for non-cylindrical sample. So if you do it in the lab, it's relatively easy. You calibrate your geometry, and then you can have a correlation, direct relation between your resistance and your resistivity. But what is the resistivity actually? The resistivity, as I told you, it depends on the way or easily the current can flow through it. And we have different types of materials in the Earth. Basically, I'm dividing those in 3 categories. You have conductors where electrons can move freely. Those have a very low resistivity. This is what you have in electrical wire. If you have copper, the electrons can move freely, so very low resistivity. At the opposite, you have the insulator with a very high resistivity. Basically, their electrons cannot move, they are not free, so you cannot flow any electrical current through them. You have plastic, for example, that kind of materials are insulators. And then in between, you have semiconductors. In those semiconductors, there are some electrons, but they are only free if they can overcome an energetic barrier. So they're going to conduct the current depending on the conditions. So let's talk about rocks now. If you look at a rock, you have some grains, you have some pores. Within the pores, you might have different type of fluids. And the question is, what is the type of conduction you might expect in the different grains? Do we have conductors? Well, there are some. Native metals, for example, copper, gold, graphite, are examples of conductors that you might find in a rocks, but they are not very common. Do we have semiconductors? Yes, we do as well. Sulfides material, sulfides mineral, for example, some oxides as well, behave as semiconductors in the rock. But again, they are quite rare. You might find them in ore deposits, for example. But most of our minerals are actually insulators. If you take silicates, quartz, for example, or carbonates, calcite, those grains, they are not allowing the current to flow through it. So basically, when we look at most of rocks or sediments, the grains, they are insulators. So you cannot conduct the current through the grain matrix. So the question is, where is the current flowing then? Well, of course, it can flow through the fluids. We all know, for example, that water is a good electrical conductor. So when we are measuring the resistivity of the subsurface, or we're trying to measure it at least, we are going to be mostly sensitive to the fluid, and indirectly, it means that we're going to be sensitive to the porosity of the rock. Which is good, right? Because for hydrogeologists, the porosity is an important parameter. But water is, of course, not the only fluid that can be present in the pore. We can have air if you're in the unsaturated zone. You can have oil and gas if you're doing oil and gas exploration, or if you have contamination, for example. Those are also insulators. So you don't have electrical current flowing through air, you don't have electrical current flowing through the oil and gas. So they can be considered as insulators, and they will behave the same way as the grain matrix. So we're going to be mostly interested into the water which is actually present in the pore. The electrical conductivity of water itself also depends on different type of parameters. The total dissolved solid content, so the ion concentration in it. The more ions we have in the water, the more easily current can flow through water. So actually pure water is not so conductive. The ion mobility itself is also going to have an influence. Not all ions have the same mobility, and they might interact with each other, but this influence is relatively limited. And then we also have the temperature, which is going to impact the conductivity. Basically, what's happening is that when the temperature is increasing, the fluid viscosity is decreasing, and so ions can move more easily, and so we will have an increase of the electrical conductivity of water when the temperature is increasing. So if we now try to summarize how the electrical current can flow through a rock or through a sediment, we might have different type of processes then occurring. It might happen if you have sulfides or you have native metals that you have metallic or electronic conduction. It means that electron can move through the grains. This will only happen if we have those type of conductive minerals or semiconductors at least. And then the resistivity, the bulk resistivity of the rock, when we say bulk resistivity, it means that we look at everything together, both the grains, the pores, the water, all together. This electronic conduction will influence the resistivity, of course, but it will depend on the type of mineralization, also the proportion of conductive minerals. Do you have 1%, 2%, 3%? And of course of the dissemination of the mineral, because if you have zones with a very high concentration of those minerals, this can produce very high preferential flow paths for the electrical current. If they are disseminated in the rock matrix and they are not connected to each other, it's going to reduce the actual resistivity of the rock. For example, if you would look at the resistivity of the galena mineral, so you take just one sample, one mineral, pure galena, you would have a very low resistivity. But if you put it in a rock matrix, disseminate it, you would get a resistivity which is much higher, because the other grains that are actually insulators would, of course, influence also the bulk resistivity. It also means that if you don't have those type of minerals, most rocks are made of grains that are insulators, and so you would expect very high resistivity. So I've seen we have a lot of granite here around. If you have a big granite block and you try to measure the resistivity, it will be super high because the porosity is very low, the grains are insulator, and so you will have a very high resistivity. In most rocks and most sediments, what you are actually measuring is linked to the electrolytic conduction. So this is the part of the current which is flowing in the water. And as I already mentioned, it will depend on the type of fluid, the saturation and the salinity, but also the connectivity of the pore space. Because this is something we have seen in previous days where we were looking at transport experiments. The water has to flow around the grains. It's the same for the current. If the grains are insulator, then your electrical current has to flow through the grain, and so the connectivity of the pore space is going to be important. As soon as you have a little bit of water in your rock, it's often the dominating processes for electrical currents. And so in the presence of water, we can often neglect the matrix conductivity. And finally, there is a third conduction processes which is also important, that we call surface conduction. And this is a process that is occurring at the surface of the grain. And basically it comes from the fact that when you have grains in a fluid, they have a surface charge. It's typically negative in normal pH conditions. And because you have charge that are located at the surface of the grain, it's going to perturb locally the concentration of the ions. So typically, if you would look at a grain particle, you have negative charge at the surface. I take an example of a clay particle in this case because clay they have a high charge at their surface. What's going to happen is that the cations that are in the water are going to be attracted towards this clay particle. You have a first layer that we call the stern layer, where the ions are in direct contact with the grain. And then we have a diffuse layer here, where we have a higher concentration of positive ions, positively charged ions, compared to the rest of the solution. And so globally, you have a higher concentration around the particles in terms of ions, which means that you have a preferential flow path for the current to flow. And if you think about the fact that water is often the wetting fluid for grains, it means that even at low saturation, you might have water close to those grains, where you have also a higher concentration, and so you might maintain a conductivity path for the current even at low saturation, both because of the wetting characteristic of water, but also because you have this double layer that acts as a preferential flow path. So surface conductivity can dominate the electrolytic conduction mostly at low salinity. So this is when you have not that many ions in water, the fact that they are concentrated there can start to dominate the process. It's also an important process when you have particles that have a high charge. And this is the case, for example, for clay particles that have a high cation exchange capacity. It will be less important in sand, for example, compared to clay. Okay, now if we try to summarize how those processes are taking place in the subsurface, and if we would like basically to get a relationship that allows us to estimate what would be the bulk conductivity of a rock sample or of sediment samples related to the different parameters that we've just discussed. And luckily a guy called Archie it was in 1942 published a well-known paper where he was developing a petrophysical relationship between the bulk conductivity and the conductivity of the pore fluid. At that time, it was for the oil industry, and basically the idea was to be able to interpret geophysical logs that were collected for oil exploration in terms of oil content and water content and that kind of things. And as you can see, this relationship is relatively simple, because basically what Archie observed is that we have a linear relationship between the bulk conductivity and the water conductivity or the fluid conductivity, and that the correlation coefficient is basically a parameter that we call the formation factor. It's called a formation factor. It means that it depends on the type of formation that you are getting. It's not going to be the same for a sand or for a sandstone or for a limestone or for a granite. And so it's going to depend on the different type of formation. This formation factor itself, I think with what I told you, you can already guess it. It's going to be dependent on the porosity. You expect that if you have a higher porosity, this formation factor is going to be smaller. Because the higher the porosity, the higher the impact of the fluid conductivity on your bulk conductivity, and so it means that your formation factor is going to decrease. The relationship with the porosity is not linear. It depends, it's exponential, and this exponent also depends actually on the connectivity of the pore space. This is called the cementation factor. It's an empirical factor, but that is linked to the tortuosity. So basically, if you have a pore space which is well connected, you will have a lower formation factor compared to a porosity where you would have a lot of dead ends and that kind of things. Then your cementation factor would increase. And finally, there is a factor here. If Damien Junot was there, he would be mad at me by showing these parameters, because in theory, it should not be there. It's a poorly fitting parameter when you try to derive an empirical law. And so it should actually be equal to 1. The reason for this parameter to be equal to 1 is that if you go to a porosity of 1, so if you have a pure fluid, then of course the bulk conductivity should be the water conductivity, so it cannot be anything else than 1. But in practice, when you are trying to fit a petrophysical relationship to some samples, you need sometimes to adjust a little bit the law so that it fits your data points, and this is why sometimes in papers you see this parameter A. But next week when Damien will be there, make sure you tell him that I told you that A is equal to 1 or shouldn't be appearing in this relationship. Okay, so that's the kind of law we can expect in a saturated medium. So when we have the pore space which is fully filled with water. In unsaturated condition, what is happening is that, of course, when the water content is decreasing, the saturation is decreasing, you have the electrical current cannot flow so easily anymore because part of the pore space is filled with air or with another phase which is not conductive, which means that the conductivity is going to decrease. So in that case, you have to add an additional factor to this relationship, which is the saturation. Again, the relationship with saturation is not linear. It depends also on an exponent, which is called the saturation exponent. And this saturation exponent also depends on the type of formation you have, so you don't have always the same value. But typically, it's around 2. Around 2 means you have 2 examples here. It can be 1.9, it can be 1.8, but typically, it's a smaller range of variation than the cementation exponent that we had here. That this petrophysical relationship, it's not a general relationship that you can apply to any context. Basically, if you want to use that kind of relationship to make some quantitative interpretation of the conductivity, you will need to empirically calibrate this for your study site. It means that you would need sample, you would need to have sample brought to the lab, make those measurements at different water conductivity, different saturation to derive the relationship. So it's a lot of work, and it's not always so easy to do, but that's the only way you can try actually to get something quantitative in terms, for example, of porosity. In many cases, we don't have that. So in many cases, what's going to happen is that we're going to stick to the bulk conductivity, and we're going to try to make qualitative interpretation. You know that in a given context, whatever the type of rock you have, if you have a lateral variation of conductivity, you might interpret this as a change of porosity or a change in salinity or a change in one of the other parameters that are influencing. So you can still make qualitative interpretation. The quantitative interpretation is only possible if you have started to derive this kind of petrophysical relationship, mostly in the lab then.
Can I ask a quick question?
Yeah.
Nowadays there's a lot of discussion about critical path analysis, and lots of semiconductors depend on having really good descriptions.
Yeah.
These are very empirical. Obviously with scattering the data, there's not a point in going really too deep, but is this still the standard state of the art, or are people going to newer models?
There are newer models. I'm coming to it later on. I'm not going to develop them today because I wanted to stay basic, but of course there are more advanced models. And if Damien was there, he could tell you more about it. But before we go further, we have to also take into account the fact that I told you in some conditions, you might have other processes. It might be this electronic conduction that you have in semiconductors. It might be the surface conduction that you have for clay. And in that case, you cannot basically, what I've shown before, here it's only based on the electrolytic conditions, so what is happening in the water. As soon as you have also other processes taking place around the grains or in the grains themselves, the one way to take it into account is to add an additional term to this relationship. And this is called the surface conductivity, but it can also encompass the electronic conduction coming from semiconductors, for example. And this would be an easy way, basically, to account for the fact that you have then a little bit of conduction still occurring in the rock matrix or around the grains at least. And then if you look at what it would give you in terms of different type of geological media or sediments. So this is just a graph showing you the water conductivity on the x-axis and the bulk conductivity on the y-axis for different type of lithologies. Yes?
When you say that the conductivity of the surface has to be sufficiently low, you mean that should be like a clay or something like that? Or do we know that we have to use these formulas?
Yeah, it depends on the context. So the geological context, basically. So if you are in a granite which is not altered, for example, you would not expect that kind of surface conductivity. As soon as it is altered, that you have clay, for example, in the alteration process of when you create clay, then you would need to consider that. And it's mostly important, again, assume that you don't have this petrophysical relationship, but you want to make an interpretation of the bulk conductivity, and you want to do it in terms of porosity. If you ignore the fact that you might have surface conductivity in some media, you might be you might be wrong. The same if you are interpreting in terms of water conductivity, let's say salinity. You can, in a context where you have only sand and that you have very low resistivity or very high conductivity, typically you can interpret this as a high salinity. But if you have also the presence of clay, those higher conductivity can also be related to the presence of clay. So it means that you cannot be so sure anymore about your interpretation. So that's the context. This is why I told you this disclaimer was about that. If you don't have the context, you don't have the additional information about what you can expect, I mean, you cannot really make interpretation about it. It just gives you an image of the variability, but you cannot really be conclusive about the conclusion. But just to show you what it gives if you have different type of sediments. So here you have an example for clay. Those two are for sand and gravel. And basically what this graph is showing you is that when you have high conductivity of the water, so this is this term which is high, you see that you have then mostly a linear relationship between the water conductivity and the bulk conductivity, and the surface conduction can then sometimes be neglected. But when you are looking at low value of the water conductivity, then the surface conductivity becomes very important. So this is what we just said. And then about your question, John, this is what I wrote here. So basically, indeed, those are the really old petrophysical relationships that I'm showing you, because they are still valid, more or less, and they tell you what are the important parameters. Of course, there has been some research about trying to generalize that. Basically, you want to avoid that you have this formation factor, so you would like to try to understand what this formation factor is and relate it to physical parameters of the pore space that you hopefully might measure with other techniques. The same for the conductor. So of course there is research about it. And basically you could write in a general sense that the bulk conductivity is basically a function, of course, of the water conductivity that remains. This formation factor, you can try to characterize it better. And with this cementation factor, basically you can link it to the tortuosity. So if you have measure of the tortuosity, for example, by using micro CT scans, you can start to be more quantitative about your relationship. And the surface conductivity would be mostly related to the cation exchange capacity, and this is the surface charge that you would have at your grain. And of course, the saturation and the water conductivity, they are actually very important parameters. Okay, and just to give you also, Marie-Lydia, to come back to your question about this interpretation, how can you be sure? Actually, you're not. This is a typical table or figure that we show to the students just to realize that there is no direct link between one value of conductivity or one value of resistivity and a specific type of rock or specific type of conditions. Because of all those factors, the fact that the water is so important, it means that if you take the same sand and that you have it in a saline context or a freshwater context, it's not going to be the same conductivity. And often you have several order of magnitudes. So if you look here, for a gravel, for example, you can have value ranging from within 2 order of magnitudes. For clay as well, for rock as well. Take a limestone, for example. If you have a very unweathered limestone, it's going to be very resistive because the primary porosity is low. You don't have a lot of space for the current to flow. But as soon as you have alteration, you have fractures, it's going to be much more sensitive. If you have karst and that those karst are filled with water, you have basically a free electrolyte solution where the current can flow. And so in limestone, you can have even 3 order of magnitudes, the same for sandstone. So you will never be able to, like if you come back to the second image that I show you, this image with colors, it's impossible to say this yellow value, it's actually a granite, or this yellow value, it's actually a sandstone. So it's impossible. You really need the context to be able to make this kind of interpretation. This is why often what you would see in the interpretation of geophysical image, it's more qualitative interpretation, making some relative conclusions. For example, in a context where the water conductivity would be constant, you would always expect the resistivity of a sand formation to be higher than the resistivity of a clay formation. So if you are in a context where you expect horizontal layers, it's what we have in Flanders, for example, we have sandy aquifers and then clayey aquitards. Then you will go on the field, you will measure your resistivity, and when you see a decrease of resistivity, you might interpret this, okay, I have found the top of my clay formation. And this might be sufficient for your purposes. And this is often like this that we actually interpret geophysical measurements. Okay, just checking the time. Okay, it should be fine. So far we have discussed the petrophysical relationship, so how we can relate the electrical conductivity to basic properties of the rock. And now I'm going to focus a little bit more on we can actually measure the resistivity on the field. And basically, if you consider that you would be at the surface of the Earth and that on a point A you would inject an electrical current, if your subsurface is homogeneous, what's going to happen is that your current is going to flow in all directions. So you would have your current flowing in all directions in a half space. And at a given distance of the injection, you would have a constant potential. And the potential would be constant along a shell that would correspond to this hemisphere. Okay? Using Ohm's law, you can actually estimate what would be the drop of potential for infinitely small distance around this shell. Assume that you have an eggshell with a very small, a very thin shell. And what would be the drop of potential in between the two if you would be injecting in the middle of your egg? So this is what we are here calculating, and this is linked to Ohm's law. So this drop of potential equals the resistance multiplied by the injected current. We have also seen that if you know the geometry of your sample, so if you know the geometry of your shell, you can relate the resistance to the resistivity. It's the resistivity times the thickness of this shell, so this infinitely small radius, dr, divided by the section of your hemisphere, of your eggshell. This section is 2 pi r squared, it's a hemisphere. And so we have an expression of the resistance that would have this hemisphere, this eggshell, infinitely small. From there, we can actually calculate what would be the actual potential at a given point M at a distance r. We just have to sum all those infinitely small drop of potential, and we have to do that from infinity, because at infinite distance the potential is 0, and you add them until you arrive at M. So this is why you calculate this integral. It's the first big equation. You have seen much more complicated than that in the past days. But if you solve this equation, we have an expression for the difference of potential, and this is what's calculated on the previous slide. So if you make this integration from infinity to M, you get an expression for the potential. It means that if you inject a current in a homogeneous space of resistivity R, you can deduce what would be the potential anywhere in the Earth, and this potential would be linked to the actual resistivity, the injected current, and the distance to the injection point. So that's for an homogeneous space. If the space is not homogeneous, then you have to solve a more complicated equation. And actually, this is the equation that we have to solve. This is called Poisson's equation. In this equation, you have the electrical conductivity that appears. This is the electrical potential. And this is basically the source of your current. This is where the current is injecting. If you look at this equation, it looks very similar to what you have solved in the past days. It's really similar to the groundwater flow equations. Basically, it's the same. This could be a source corresponding to an injection of fluid, for example, or an extraction of fluid. The conductivity could be the hydraulic conductivity, and you would have basically the same type of equation. So if you can solve groundwater flow, you can also solve electrical flow. Typically what we do is to solve this kind of equation then with a numerical method. It can be finite difference, finite element, finite volume. It doesn't matter, and we can solve this in 1D, 2D, or 3D. Nowadays it's not a problem anymore to solve that kind of equation. Now, In reality, we never measure with just one electrode. If you remember your practical class at high school when you were doing your physics practicals, you always use difference of potential actually. So you need at least 2 electrodes to measure this, and the same to inject a current, you need 2 electrodes. So we never use only 1 or 2 electrodes, we always use quadruples. We use actually 4 electrodes at a time. And what we do is to inject the current between 2 electrodes. And in theory, you could also measure directly the potential that is needed to inject a given current between those A and B, and this would give you a value of the resistance. But it's not very practical because it's dependent on too many factors that are not related to the Earth. So what we do is to inject the current and we measure the potential between 2 other electrodes that we called M and N. Now, of course, it makes things complicated because as soon as you have 2 electrodes, your current is not flowing anymore along hemisphere. But thanks to the superposition principle, we can still deduce what would be the voltage at a point resulting from an injection between A and B. It would just be the sum if you would just inject at A and just inject at B. So we can sum the potential at M, we can sum the potential at N, and then we take the difference between the two. This is what we measure. And we observe that this difference of potential would also be related to the resistivity of the ground, the injected current, and this is purely geometric. It's a geometrical factor that only depends on the relative distance between the electrodes. For example, RAM is the distance between A and M. So basically we have no way with our 4 electrodes to estimate the resistivity. You go on the field, you put your electrodes on the ground, you know the relative distance to each other, you inject a current I, and you measure a difference of potential delta V, and you get an estimation of the resistivity of the ground, which is going to be equal to that. K is called a geometrical factor, as I said, and the resistance is just the difference of potential divided by the injected current, 2 things that you actually measure with your system. Now again, this is valid if your half space, if your subsurface is homogeneous, which is typically not the case. We never have an homogeneous Earth. So the resistivity that you measure here is not the actual resistivity of the ground. Actually, it's what we call an apparent resistivity. It's the resistivity that a homogeneous Earth would have to give you exactly the same measured potential or the same measured resistance. So it's just something abstract that doesn't exist, but that is what you measure on the field. We have different ways to calculate those geometrical factors. I'm not going into the details in here because there are many different configurations that are possible. Just you have to be aware that the way you place your electrode has an impact on the geometrical factor. The higher the geometrical factor, the lower your signal to noise ratio. And this comes from the fact that if your geometrical factor is high here, you would tend to measure lower potential. And if you have a given noise level of a few millivolt, if your difference of potential is low, it means that it might become lower than your noise, and then you will measure just noise instead of measure a signal. So you have to be aware that when the configuration of your electrodes can have an impact on the data quality. Okay. In an homogeneous space, the current flow are just always relatively homogeneous. But if you have a layered Earth, for example, it's not going to be the case anymore. Assume that you have a resistivity of 30 ohm meter at the top and then a higher resistivity at the bottom. Your current lines are going to concentrate in the first layer because the resistivity is lower, so current is flowing more easily in this first layer, which means that not a lot of current is going to go into the second one. Assume that now you have the opposite. You have a high resistivity layers here and you have a lower resistivity layer below. Then the current is going to try to go quickly to the second layer where it can flow more easily. Again, it's the same if you have a high hydraulic conductivity layer in the ground, right? This is where the ground underflow is going to happen. Now, this also impacts the depth of investigation. Because you're measuring from the surface only, it means that you always have a decrease of your resolution with depth. You cannot expect putting 2 electrodes 5 meters apart to measure something which is 3 kilometers depth. So this is not how it is working. So it means that if you want to go deeper, you need to use larger spacing. But it's impossible to predict the depth that you are going to reach because it depends on the distribution of resistivity. In this case, in which of the two cases do you think we have a higher depth of investigation? Yeah, on this one. Because in this case, the current is flowing just in the upper part, so basically you have no sensitivity. And probably if you measure here with relatively small spacing, you will never get the actual resistivity of this layer. You're not going to be sensitive to it, you're just going to be only sensitive to the first one. While here, because the current is trying to go there, you know that you have a lower resistivity layer at depth, and so your depth of investigation will be actually a little bit larger. Okay, maybe you have seen us working with the group doing geophysics yesterday and on Tuesday, so we're measuring on the field. This is the kind of equipment you need for ERT. You have small electrodes that you put into the ground. You have cables to connect those electrodes, and then you have what we call the resistivity meter or thermometer, which is basically both a transmitter that allows you to inject the current and a receiver that allows you to measure the difference of potential. So basically it's an ampermeter and a voltmeter combined together. And what is important is that we have a switching unit, because you can imagine that if you have to go, this is what was done in the past, 1 century ago, when people were going on the field, they were moving with their 4 electrodes a little bit everywhere, and they were measuring then at different locations. Now we have switching units. You just give a sequence of measurements to your system and it's measuring automatically, of course. How is it working? Well, you have 2 ways of measuring, 2 possibilities. You can do what we call profiling. And profiling would be basically using the same configuration. So you decide for a given configuration, and then you move your configuration along a line. And if you have an anomaly somewhere, in this case an anomaly with a higher resistivity, you would see that your apparent resistivity would be increasing when you are going to measure above it. Okay? So that's profiling. You can also do sounding. In a sounding, basically the idea is that you would start with a given configuration, and then you would increase the distance between your electrodes, and so you will sense deeper and deeper into the ground. In this case, you have the resistivity of the second layer, which is higher, and so you would see that your apparent resistivity is increasing with depth. Now, of course, what we do nowadays in electrical resistivity tomography is basically to combine both. So what we do is to install our electrodes at the surface. Typically, we work with a few tens of electrodes. Between 40 and 100 are typical numbers that we use. And then you're going to use different combination of those electrodes along a line, and also higher spacing, which means that you are going to sense at different depths, different location, and this is what we call the tomography. And so you will combine all those configurations to get a data set which is sensitive to both lateral variation of resistivity and vertical variation of resistivity. And you get an image which is called a pseudo-section. A pseudo-section is just a 2D representation of your data set where you put the value of the apparent resistivity for a specific configuration at a given location in space. You cannot interpret a pseudo-section. While you can know if you have anomalies in it. Here you see change of apparent resistivity, so it means in reality you have change of the apparent of the resistivity into the ground. But those are 3 pseudo-sections obtained for just 3 different ways of measuring, and you see that they are completely different. It means that you cannot actually interpret this in terms of real resistivity. It's just a 2D representation of your data set. To be able, before we go that, but to be able to make an interpretation, we'll need to process our data set to make, we have to make an inversion, basically. Just quickly a word about the depths of investigation, because it's often the first question you have. So when you go on the field and you want to image something, you have an estimation maybe of the depths you are looking at, and based on that you will have to design your survey. Am I going to do a line which is 100 meter long or 500 meter long? If you have to go deep, you need to go for the larger distance. So it's often interesting to have an estimation of the depth of investigation, but I told you already that it depends on the actual resistivity distribution, so you cannot know in advance. So typically what we do, you have two possibilities. You can use a rule of thumbs. Often we estimate that the depth of investigation is between 1/10 and 1/5 of the length of the profile. So this can be a first target. The second option is, if you know a little bit what you can expect, is to make some forward modeling before you go on the field. I just told you we need to invert the data. And why is it? It's because if you would just look at the pseudo section, it would be something like this. Sometimes it's a little messy. Because it's really just looking at data. And in data, you might have sharp variation at short distances. If you do an inversion, then you get actually a picture of an estimation of the resistivity with the ground. So this is the inversion that would correspond to this pseudo section. And this can be actually interpreted in terms of lateral variation of resistivity. Actually, this figure is coming from a saline context, and the low resistivity, they correspond to the presence of salt water. So this is really important to go from this, the data, to the inversion. So this is a very important process, and it's not only for ERTs, for most geophysical methods that we need to do this inversion. So it's important to know how it works, but also to know the limitations. I would say that the limitations are more important actually the process itself, because if you know the limitations, you also avoid overinterpretation of your data. How does it work? Well, typically you would discretize your subsurface into cells, like you would do for groundwater models, for example. And each cell could have a value of the electrical conductivity. In this case, you have an example where we also have electrodes that were installed in boreholes. So this is also a possibility. If you're on the electrode at the surface, you would just have a grid along that would extend to the location of the surface electrodes. You can also do it in 3D. Assume that you collect data in 3D, then you would just have a 3D grid. When you just measure along a profile, during the process, often we make an assumption is that the resistivity across the line, so perpendicular to your line, is not changing. So it means you assume that you are perpendicular to the geological structures. In 3D, of course, you will simulate the current flow in 3D. So actually we have two problems when we try to make an inversion. And the first problem is that we need to be able to solve Poisson's equation. Basically, if you would know the distribution of the conductivity into the ground, if you are able to solve Poisson's equation, you are going to be able to deduce what would be the measured voltage for your specific electrode configuration. This is called the forward problem. What we have now is actually the opposite. We have been on the field, we have collected data, and we want to go to an estimation of the model resistivity. This is actually the inverse problem. And actually to solve the inverse problem, we need to be able to solve also the forward problem. This inverse problem in geophysics is really not easy to solve. There are different reasons. The first one is that when you start making this grid, you see that you have many unknowns. You have a value of conductivity in every cell. And it's often the case that you have more unknowns than actually data. You have an unknown value of conductivity in every one on your cell, and you have a limited amount of data. So your problem is often underdetermined. You also have data that are noisy. And that can be problematic, because if you push your inversion too far, you start modeling noise. It means that a small change in your data can give you instability in the solution. This is something you want to avoid. And because of that, also the solution of your problem is non-unique. I'm going to illustrate that at a later stage, but you can find many different distribution of conductivity that can explain your data. It's the same when you calibrate a groundwater model. If you give the same data set to two hydrogeologists, they will come with two different models that can actually explain the data probably to the same level. So the solution is non-unique. I would say the difference between geophysics and groundwater is that still we often have a little bit more of data. And that if you would just invert the data in a least square sense, often we would get something which is not realistic. Because we would produce like artifacts or very localized anomaly that are not really what we expect in a geological context. So to solve this problem, the mainstream solution, I would say, is to add some constraint to the solution. This is called regularization. Mathematically, the regularization is stabilizing the inversion. It makes it more stable, less sensitive to noise. And it also allows you to impose some prior assumption that you would have on the solution. For example, assume that you know that you expect sharp variation. You can tell to your model, I want to find sharp variation. Or at the opposite, if you think that you have just a smooth variation, you can impose that you have those smooth variation in the image. The common choice, and it's a default choice in all inversion software that are available for geophysical data, is to impose a smoothness constraint solution. What does that mean? It means that you would try to find the solution with the less possible change. So you will only have small gradient in your final image. So something which is very smooth. I don't know, historically this is the most used solution, but if you think about geology, often geology is not very smooth. Often geology is actually more sharp or more complex than that. But by default, it's the most used solution in all software, so be careful about that. When you start making solution, it might not be the best choice. How does it work in practice? A little bit more math. We define an objective function, basically, which has two terms. This is just a data fit term, and so this is the difference between the simulated data and the observed data. This is a matrix which is weighting the different data. So if you have data that are more noisy, you can give them less weight. And you have a second term here, which is the regularization. So this matrix is setting some prior assumption. For example, it can be the calculation of the gradient in your distribution of model parameter, and then you will minimize the gradient. It will give you something smooth. So this is a way to invert the data. And the lambda is a regularization parameter which is balancing between the two terms. Okay? The inversion process itself is then solved typically with a Gauss-Newton scheme. You start from an initial estimation of your model parameters, so in this case the electrical conductivity. Typically for ERT you would take the average apparent resistivity that you have measured on the field. You calculate a sensitivity matrix or Jacobian matrix, which is basically a matrix telling you how the data would change if you would change the value of the conductivity in one single cell of your model. And so it's a Jacobian matrix. And then you can calculate by the Gauss-Newton scheme an update to your model parameters. You see it's relatively complex. It involves the Jacobian matrix, the data weighting matrix, and the regularization matrix. And then you calculate an updated model. And you iterate until you converge to a solution, which is typically when you cannot improve your model anymore, or you have reached a maximum number of iterations, for example. Okay. You have seen in this equation, we have the Jacobian matrix or sensitivity matrix, which is important. This is something you get anyway at the end of your inversion process, and this often looks like this. So it's an image where you see that you have high sensitivity at the top and lower sensitivity at the bottom. it represents the fact that the deeper you go in your model, the less sensitive your data are to the system. It's because you're measuring only from the surface. And so you are having a resolution or sensitivity that is decreasing with steps. In this case, you also see, this is the corresponding inversion. You see that you have here a value with very low resistivity. It again corresponds to a case where we have salt water. This is highly conductive, so this is concentrating the current lines. So what is happening is that below you have a more resistive bedrock. And actually you see that it corresponds to a sharp decrease of sensitivity. What does that mean in this case? You get an image, your image is going down to 80 meters, maybe you are happy, I have a depth of investigation of 80 meters. Actually, it's not the case, because you're not sensitive at all to the value of the bedrock. So how do you interpret this? Well, you can interpret that you have a sharp increase of resistivity, that you know, but you cannot interpret the value of the resistivity that you get in this bedrock. You are not sensitive to it, yeah?
So here we see kind of a typical artifact of a line which is
this?
Yeah. And let's just say that was due to an electrode that made poor contact.
This is probably because we removed data points.
Okay.
Yeah.
So the question I have for you,
yeah.
you did your inversion discussion,
yeah.
but we acted as if all the electrodes had equal good contact with the medium.
No,
is
well,
there some sort of multiplier we use?
Yeah,
to kind of
you can use this. So this is a data weighting matrix.
Okay.
So you can say, okay, if my data are less good, or you assume your data are less good, you're going to decrease the weight given to this data point. And so it's going to influence less your inversion process. So this can be taken into account.
If we throw out that that's minimizing how much we take into account, we can also just simply do a linear adjustment, say that, oh, this one had higher contact resistance, adjust all the data up rather than diminishing its value.
Yeah, you can, I mean, you're free in the way you're doing that. But then the idea, what I would support is that you're doing it in an objective way, of course. And it's trying to be as objective as possible, which is not always so easy. Typically, we make an estimation on the field, so we repeat the measurement several times. It's called we do stacking. This gives you an estimation of the error, or we can do what we call reciprocal. So reciprocal is switching the injection electrode and the potential electrode, and this gives you also an estimation of the error. And then you can use that to weight your data. And often what we do, we're not really relying on just the single value of the error, but we build an error model, which is typically a model which is showing an increase of the error with the measured resistance. So this is the typical way to do it. Of course, it means it takes more time on the field. Stacking is always done, but reciprocals it's double the time of that acquisition, so it's not always done.
So how do you weigh the electrode contact, the diagnostic that you run with the syscal to?
Basically, the electrode contact is going to. You have two ways to do it. You check the electrode contact with with the instrument initially, and if the electrode contact is too high, you're going first to try to solve this. For example, you're going to try to improve. So you can put your electrode a little bit at another location. You can try to increase to decrease the contact resistance by, for example, pouring a little bit of water on it. So that would be your first solution. Second solution is often you see a correlation between the contact resistance and the stacking error. So somehow the fact that you have lower contact resistance is going to be translated into lower data quality. Okay, just to give you a taste of the importance of regularization, there are a few examples where I'm showing the same data set but inverted with different type of regularization. And you see, this is like just a smooth inversion. So you see very gradual transition, and this is a very sharp transition where I impose basically that I should have blocks in my solution. And maybe qualitatively, they're the same. I mean, if you would make an interpretation, you would probably just interpret this as a low resistivity zone. But if you are interested in where this contact is, maybe using a blocking inversion is actually much better. This is another example. This comes from my PhD thesis, actually. And those are 8 inversions with different type of constraint that I'm using. And Some of them looks quite different. If you take this one and this one, for example, I mean, this one is very resistive everywhere, but they are all fitting the data to the same level. So it tells you basically that this and this are equally probable. I know that this is probably not true because I have prior information, I have boreholes, so then it can guide you into choosing a better inversion. The key here is that the best inversion for one case might not be the best inversion for another, because again it depends on the context. So you have to be a bit careful about it. In this case, the best inversion that we got was by imposing the depths of the bedrock that we had measured with another geophysical technique. With seismic method, we knew how deep the bedrock was, and we imposed this during the inversion, which helped us to better characterize the upper part of the model. But this requires a little bit of expertise to do that kind of things. Yeah? Yeah?
What would be the value of doing like a bunch of different inversions and then take the sort of the stochastic probability?
It's a good, I mean, here I showed you mostly the deterministic kind of inversion. Stochastic inversion remains quite difficult because it's difficult to define a good prior distribution if you would do really stochastic inversion with MCMC. There are a few examples in the literature, but you really need to know very well the kind of things to expect. I think there is a big value in trying, when you invert the data, trying different type of regularization. It's not stochastic in the sense that you're just going to do maybe 10 different, but it will give you at least a range of what would be possible. And there are actually regularization that allows you to do that relatively simply. Yeah, so I would say always try different type of regularization. It's not so costly, it doesn't take that much time. And in this case, how we choose the best is just by looking at ground truth data. So this is again what I told you before. It's really important to be aware that we need some more data to interpret this. I have to speed up a little bit, I see. Just to give you also a feeling of what the inversion is doing, this is like a 3D model with like very sharp contrast. And when you simulate this synthetically and that you invert the data, you see those gradual deformations. So you really have to be aware that the inversion is like looking through a filter. So it's not giving you the truth. It's just giving you an estimation of the resistivity distribution. Just a few examples of contexts where ERT is really useful. This is saline context I showed you already. And we see here the blue value, low resistivity corresponding to salt water. This is an interesting case because we have fresh water underneath. An example where we detected a fault, as you see a contact here between a value with different resistivity. This is the detection of fractures in limestone. So you see unweathered limestone here and then big fracture zone that were imaged to look at where we could install pumping wells, for example, for groundwater. This is the detection of the bedrock. So if you relate to what Camille showed 2 days ago, this is the kind of thing that you could do in a catchment with volcanic rocks to define where is your basalt, for example. This is a 3D example when we were trying to look at where was the unweathered limestone. It was to install a wind turbine in this case. So we wanted to not to put it on a karstic features, basically. And this is again saltwater intrusion, where we didn't do 3D, but multiple profile just to characterize where the saline zone was located. This is an example where we also managed to interpret quantitatively the data, because we had some previous studies that had estimated the parameters of Archie's law. So we were able to go from the conductivity or resistivity towards the total dissolved solid content. Which was in this case very high. It was corresponding basically to the value that we have in the sea. I want to talk to you at least a little bit about time-lapse application, because we have seen so far a lot of processes that are dynamic if you think about transport or groundwater flow. And a geophysical method can be very useful to monitor processes, because if you go back to the petrophysical relationship that I told you, if you are on a site where you can assume that the geology is constant, it means that your formation factor is going to be the same for at least a human perspective, right? You don't expect weathering to occur in just 2 days if you are at the field scale. It means that if you are interested into a change of saturation or a change of water conductivity, and that you repeat measurements in time, you're going to be very sensitive to those changes. And you are going to be actually much more quantitative when you look at changes than when you look at the absolute value of resistivity. And good targets are saturation, salinity, or temperature, actually. I'm just going to show you an example where we used a heat tracer, and we basically calibrated the change of conductivity that we could expect from the temperature first in the lab. So we took our water samples, we look at how much the water conductivity was changing with the temperature. It's actually about 2% per degree Celsius. And then we assume by taking the ratio of Archie's law between 2 times that we were able to deduce the value of conductivity at time 2 from the water conductivity and the bulk conductivity at time 1. And if you introduce this relationship, because the fluid conductivity we measured in the lab, so by introducing this, we were able to deduce what would be the temperature from the bulk conductivity that we are measuring on the site. This was a tracing experiment, so we injected some water here, and we were measuring here with cross-borehole data the tracer flowing through. I have time to do the electromagnetics, but I might finish just by saying a few words about the coupled inversion, because basically as a geophysicist our objective is generally not just to produce an image. We want to bring data to the end user, to hydrogeologists that might use those kind of data to have better model of what is happening at the subsurface. And you can do that sequentially. You can just give your image. It might help for building your groundwater model, for example, to set the layers and so on. But if you have dynamical data, you could also think about using those data to calibrate your groundwater model right away. And this can be done basically because if you have a petrophysical model and that you want to couple a groundwater model with a geophysical model, you can assume that you are at the sea and that you have a model of saltwater intrusion. If you know at some point that you have a given value of salinity and that you have an estimation of your petrophysical parameters, you can deduce what would be the bulk conductivity. It means that you can also simulate the collection of geophysical data, and if you have collected those, you can see if your groundwater model fits also the geophysical data that you have collected. And then basically you end up with a coupled model where you are running your groundwater model, you use your petrophysics to simulate the geophysical data, and then you can look at the misfit between your simulated and observed data and geophysical data, and then you repeat 1 to 4. So it's also an inversion process, but where you include both your hydrological data and your geophysical data. The big advantage is that if you do that, you bypass the geophysical inversion itself. So you bypass the regularization that is distorting your actual resistivity distribution. And so this is something which is possible, but which is not so easy because, of course, you need to know the petrophysics, which is often quite uncertain. This is here an example of one of my former colleagues who tried to invert, it's a synthetic case, but tried to invert both data together, groundwater data and geophysical data. And basically he was making a comparison between an uncoupled case where you would just estimate the salinity based on the geophysics, it's something you can do, or the coupled system. And in this case the main difference was that, and you see it here, it's the dispersivity. And you see that with an uncoupled approach you simulate a very high dispersivity, which is coming from the fact that you use an inversion that is smoothing stuff. And if you couple two, you get a dispersivity which is much more realistic because you bypass the regularization of your geophysical data, which is, of course, interesting. And I wanted just to say a few words also about the fact that you can also completely bypass inversions. This is a technique that we have been developing where we basically try to replace the inversion itself by a machine learning approach. What is happening is that often in earth science, for machine learning, you miss the training set. and because you have often only just one observation or just a few observations. And in a few papers, we try to bypass this issue by generating those training sets synthetically. So basically, you use models to train machine learning algorithms so that they are physically constrained, so that when we actually collect our real data, we can directly go to a predictions. For example, you can go from geophysical data into a temperature distribution right away without having to invert. Of course, you are then sensitive to the quality of your training set, and you have to be sure that your training set is good. So I'm not going to show you the details here, but then we use what you were just asking. So we use stochastic simulation to make with synthetic case to make a link between geophysical data and anything you might want to predict. For example, a temperature distribution. We have our machine learning part, and then we end up with a stochastic prediction of our system. And this is a way to bypass things. If I go back to my heat tracing experiment case, I can go directly from the resistance that I'm measuring on the field towards a temperature distribution without making any inversion, and I get image right away. And I have multiple samples in this case because it is a stochastic process. And you recognize the same type of results. Again, you need a petrophysics to be able to do that because I'm coupling a groundwater model with a geophysical model in my training step. So you still have the petrophysics, you still have the physical models that are needed. So it's solving just part of the problem and not everything. Okay. The nice thing is that you can start to predict also in the future. So in this case, I was using my tracing data to predict how would the heat storage continue in time. So for example, I had a tracing experiment of a few days, and I was using this to predict the heat storage for a month. And then you bypass completely your classical calibration prediction process. And it's straightforward to integrate geophysical data in that kind of things. I have 10 minutes left just to introduce you also electromagnetics, which is nice because I think it's really nice to talk a little bit about electromagnetics. The good thing is that all the petrophysics remains the same because electromagnetic methods that are sensitive to the electrical conductivity as well. So all the petrophysics is the same. It's just the principle of measurement which is a little bit different. And we started today by talking about Ohm's law. And probably in your physics course you have also seen another law, which is the Faraday's law of induction. This law tells you basically that if you have a changing magnetic field around an electrical circuit, you're going to induce some current into this electrical circuit. So here you have a coil of wire, and if you rotate your magnet around it, you'll generate an alternating current in the field. And the same if you would induce an electrical current into your circuit here, your magnet would rotate. I'm sure you all did this in your practical physical course, right?
You drive a car.
Sorry?
When you drive a car,
Yeah, exactly. And in geophysics, we use exactly the same. So basically, we are going to generate a primary electromagnetic field. It can be using either an alternating current or a transient electrical current in a transmitting coil, which would be here. This would induce some magnetic field in the ground. And if you have conductive stuff in the ground, you will generate then electrical current in those. Those electrical current that are also alternative current are going to generate a secondary magnetic field that you can detect then with a receiver. And basically, the response that you would get at the receiver loop is telling you something about the conductivity distribution. If you compare to ERT, the main advantage here is that you don't need a direct contact between your electrode and the ground. For ERT, you need to put your electrode in the ground. It's time intensive. While here, you just come with a coil and you don't need a contact. You can do that with the ground here. And basically what's going to happen is that you will have a delay. Well, the secondary magnetic field, it's a vector, but you will be able to detect it and to say something about the conductivity. I'm going to skip a little bit some of the thing. You have basically two ways of measuring. You can have frequency EM. In frequency domain EM, you're just generating an alternating current here constantly, and you measure a constant response here at your receiver. And what is happening is that you will have a shift between your primary field and your secondary field, and you can deduce. I'm going to go relatively fast. I'm skipping that. But you can get a direct relationship between the ratio between your secondary and primary field, which will depend on the electrical conductivity. So basically, you can get a value of your electrical conductivity if you do that. Skipping a little bit. So this is how it looks on the field. So this is the EM34 system for geonics, where you have two big coils, so you have to be two to do that. And then you would measure something related to your conductivity. It can be at large distance, so you can go relatively deep. This is another system where you have multiple coils in this pipe, and so you can measure multiple measurements at the same time that are sensitive at different depths. This you can walk with, or you can also try to mount it. For example, I don't know if I have a figure, but you can mount it on a vehicle, and you can collect data relatively easily because you measure almost constantly and you don't need any contact, so it can be relatively fast. Let me show you an example. We collected that kind of data on the beach in Belgium. Actually, this is the intertidal zone, and what we're measuring here, you see a value with a lower conductivity here. The scale is going from high to low. It corresponds to a discharge of fresh water on the beach, and you were really able to map the footprint of this discharge relatively well by using this electromagnetic mapping. It just took us like 1 day to collect those data, so it's very, very nice using a quad. When you have multiple coil combination, you can also try to make an inversion. Often you do a 1D inversion in this case because you have limited data, but it can give you a profile of the conductivity with depth, so it's possible also to make inversion. Often it's in 1D. Or if you do it in 2D or 3D because you have a big data set, you use a 1D forward model because it's much faster to solve. It can also be airborne. You have airborne frequency EM, so you can fly with an helicopter. You have this cigar under your helicopter with multiple coil, often with multiple frequency, and then you can get also 1D model of the conductivity with that. And then you map and you get nice maps. Maybe you have seen that it's really popular now in hydrogeology to map your aquifer with airborne EM. And then the other principle is to use time domain EM. The idea is a little bit different, is that you will generate a current in your loop, and basically when you switch this current off, you have a transient part of your current. So this is a transient current which is also going to generate an electromotive force into the ground, and you will have eddy currents that are going to propagate with depth, and you can record again the secondary magnetic field with either with the same loop or with another loop, and you will get a voltage decreasing with time. The difference between frequency EM and time domain EM is that with time domain EM you're not measuring the primary field. The primary field is shut off, so you have more sensitivity to the secondary field. And then the way it is going, I'm just skipping a little bit, is that you can again invert your data. So it's the same principle of inversion, and you get a 1D model of the resistivity with depth by inverting this decay curve that you measure in transient EM. One issue that we have with time domain EM is that solving the forward problem in 2D or 3D, it's really computationally very expensive because you have to solve those Maxwell equations that are very complicated. And so often we are sticking to a 1D forward model, so we assume for each sounding that the Earth is 1D, and then we look at, during the inversion, we combine all those 1D forward models together. So of course it introduces a little bit of error in it, but it's basically the only way we have to solve this problem. And then you can get that kind of nice section. So this is it's from Danish colleagues, where they map the variation in resistivity of different layers. This is probably their clay with low resistivity. This is an example of a toad system, also from the Danish colleagues from Aarhus, allowing you to really map the variability of your aquifer. It's very fast. You can do kilometers of lines per day, so much faster than ERT. And again, you can fluid from the helicopter. And it's an example from the Belgian coastal area where we collect airborne EM data. We get a resistivity model, but again, it doesn't tell you what's the salinity or anything. But if you have also a lithological model, knowing where you have clay formation and where you have sand formation, you can hope to transform your resistivity into a salinity model. And then to produce a map like this that is showing you the expected depths of the saltwater intrusion in your coastal area. So I went very fast for the EM. So if you have questions, feel free to ask them. But I think it's important to show it because you see more and more application of especially toad and airborne EM applications, because it gives you a lot of information about like the structure of your aquifer. So for hydrogeologists, I think it's probably the future of geophysics, going into those time domain electromagnetic methods. Thank you for your attention, and I'm happy to take all your questions. Yes?
Thank you for a very nice talk. May I ask two requests, small ones? One is tell us what you didn't talk about in terms of geophysical methods.
Yeah.
And if you can maybe share your vision about the future of hydrogeophysics, because you mentioned machine learning, but it could be other application, robotic ERT and whatnot.
Yeah, so there is a big part of geophysical method linked to seismic methods, of course, which is giving you a lot of information, also structural information. Of course, seismic reflection on land is difficult. It's much more common in marine geophysics, but still you can have a lot of information, especially if you have to go deep. Seismic refraction as well. Often they are combined, and because you're also sensitive to the porosity, typically with the seismic velocity. And more in seismic methods, I think the expert is Ludovic Baudet in France. With the surface wave analysis, you can also start to get sensitivity to the water. And so there is also a lot of research going on seismic methods to get information for groundwater related issues. So of course, seismic methods, it's like a different world, but it's also, I mean, I would say it can be interesting to also look at those. You shouldn't limit yourself to ERT. Just to illustrate, if I'm coming back to this example that I showed, this is actually the work of one of my PhD students. I think this is this one, not this one. It's this one. So we were interested actually into the discharge of fresh, this is a dune area, so it is a freshwater aquifer. And water is flowing from this dune aquifer towards the sea and is discharging in the sea. And basically what we have tried to model that with coupled model and so on, and the only way to explain the distribution of resistivity that we see is to start putting some heterogeneity into the aquifer. The problem is that this heterogeneity is coming from clay layers. And when you use only electromagnetic method or electric methods, you don't see the clay because the salinity is dominating the signal. So you cannot detect clay layer very easily in saline context. Even if you try to go to induced porization, it's difficult. And now we are basically moving to seismic methods with the hope that the seismic methods that are not going to be so sensitive to salinity, but much more to the lithology itself, are going to help us to discriminate that. And often using just one geophysical method might not be enough you might want to use several ones to use the advantage of the different ones. Of course, you have also GPR, for example. For shallow application, it's really interesting because you can, for example, for soil research, when you want to go deep, you have the disadvantage that the signal is vanishing very fast, so the amplitude is going down. But you can also use it cross all GPR with full waveform inversion, and you can get, it's not included in my presentation, but you can get centimeter scale resolution. Now what they're doing, for example, in Jülich with full waveform inversion, they can detect beds between boreholes of 5 to 10 centimeter thickness. So it's amazing the resolution that you can get with that kind of techniques. Of course, you need boreholes to do cross borehole GPR. And the advantage is that in the vadose zone, of course, GPR is sensitive to the dielectric permittivity, which is highly influenced by the water content. So it's very interesting also to look at GPR. I mentioned NMR in the beginning. It's probably one of the toughest because when you do NMR from the surface, you are limited to using the Earth's magnetic field to measure. And this is very tough because it's not a strong magnetic field. What they do in hospitals is that they have big magnets that are helping them to create the signal. But I know that both in Germany, in LIAG, I think, and at Aarhus University, they are now working on NMR system which have, so for shallow investigation, when they can then have their own magnets to strengthen the field, and then you can get also information on the water content, which is interesting for hydrogeologists and vadose zone soil scientists. The water content is so important, and NMR is the only method which is directly sensitive to the water content. So this is also interesting. And then your second question was about the future of hydrogeophysics. Well, of course, you can go into different directions, but I think to me what is important is that as geophysicists, we are working hand in hand with hydrogeologists to do things together and to make sure that we integrate as quantitatively as possible our geophysical data into the groundwater models. And in my group, this is the type of things we are developing. So, for example, the future is probably to try to integrate those airborne EM data into catchment scale model for hydrogeology, because it's a source of information which is so important, and it's a little bit a pity to do it in 2 steps. Just using it for like the structure, you say, yeah, maybe you can do better than that. So yes, it's the future. And I also like the time-lapse application when you are more localized on the site. We have a site currently in Iceland, and we were very lucky because we started monitoring 18 months ago. It's an hydrothermal site. And then since last summer, we have the volcanic eruptions in Iceland that are just 15 kilometers away. And actually we see changes in the hydrothermal activity on our site linked to the eruptions that are occurring at 15 kilometers away. So we were very lucky that we could get the signals, and we have very amazing data there. And I think when you look at the dynamic, you can really get most out of your geophysical data because you're sensitive to variations, which is much more easy to quantify than the absolute value of the geophysical parameter. There are two, yeah, you and then you, yeah.
Yeah, you mentioned machine learning trained on artificial data sets.
Yeah.
Right. Have you looked at deep learning to remove this kind of dependence on huge training data sets that might even lead to like hallucination and stuff like that?
I think it's definitely a way to go, but I'm always a little bit skeptical because, I mean, there are papers, if you look in the literature, there are papers trying to go directly from a data set like a resistance data set to a resistivity distribution, but it's often you have to be trained to something you know very well. So you really need to have a training set which is quite small and quite really consistent with your field data. So you cannot start from nothing. What we propose with those groundwater models that are training or data sets is that, for example, if you have many distribution of hydraulic conductivity and that you simulate a tracer test, you will have completely different distribution of temperature, very, very different. And still by training that, I would call it physically based prior, then you are able to retrieve the temperature distribution. And it's a way to include the physics in your training set instead of including just concept. But there are also like neural networks that are not physically constrained at the end of the chain, so it's probably possible with that kind of machine learning approach to get the same type of result as we managed to get. Yes?
Thanks a lot for the nice talk. And also the thing that I'm interested in about this machine learning based these applications. And you said that something about that you've already done work based on this machine learning, right?
Yeah.
Yeah. So I'm interested in which kind of models you choose. For example, it's like the physics
for the training.
Yeah.
Yeah. So we generate our training set using numerical models that are physically based. So, for example, for the tracing experiment I showed you, we just simulated our tracing experiment using hydrogeosphere, actually, in this case. And it was in collaboration with Maria. And so you simulate your training set, but you don't know what's the distribution of hydraulic conductivity. So you generate many simulations, and for each simulation, you will have different temperature distribution with time. And for each of those temperature distribution, we simulate the geophysical data that we would get. And then we use those geophysical data to train a model between, so I'm using my data to predict the temperature distribution. Yeah.
I'm asking that which model you choose to train.
And then, yeah, that's the beauty, because actually what we do is we first reduce the dimension. So you take your temperature distribution, it's relatively smooth, because if you look at the heat transport processes, you have often smooth distribution of temperature. So even if you have thousands of cells, many time steps, you can condense this information into just a few dimensions. If I remember well, it was about 10 to 15 dimensions. So we use just principal component analysis to that. And then we do the same for resistivity data, and we end up with building a relationship between two datasets that are about 10 to 20 dimensions. And in this specific example, we used canonical correlation analysis, which is a linearization technique to make the link between the two. But you could use a simple neural network as well to do that. Now what we're trying to do is to use probabilistic neural network to get also the uncertainty out of it.
Have you tried that to using the neural network to train your?
Yeah, but that's so we don't want to go, we really think that the dimension reduction step is important because it simplifies your neural network. We have tried that, it's working. Yeah, you can directly use a neural network as well.
Because that we are doing the things that based on this deep learning, the neural network for build the circuit models for reactive transport models.
Yeah.
So yes, we using this is basically from the neural network. So I'm asking that if you have the similar or choose a similar model and get some results, and I'm wondering that if you benefit from this physics informed neural network or this kind of.
I think it's anywhere worth investigating. What we have, I mean, for example, with canonical correlation analysis, there are strong limitations that at some point you are stuck. So you can predict something, but not everything, while neural networks are giving you more freedom and more possibilities. So we have had success with both. But I would say it's not always, but that's more a personal point of view. And I had a student doing that, is like always going first to the complicated stuff. And then I was asking him, but can't you just do PCA and then a linear relationship? And sometimes it's working. And then it's a killer to go to the deep neural network that you train. It's complicated, while you can just use simple techniques to get the same results, right? So we use the probabilistic neural network when it's not working as we want with the more simple technique.
I think that we should improve the models to fit our areas to get more good results.
Yeah, but I mean, it could be a big discussion, right? Next time you have to organize something about machine learning.
That's a very good question. Is there any good questions for Abdullah?
If you're in unfamiliar place, you don't know the lithology, geological background, what would be the first method to go in order to complement electrical measurements?
It depends. I mean, if you decide to do first ERT, you make an inversion and you look at your data and then you think about what to do next. If you're really blind, so I would say it really depends on the context. But a typical combination is to use ERT with like seismic refraction that are good complement to each other. Yes.
Thank you, Thomas. Maybe we can continue the discussion.